Okay, so we are kind of picking up where we left off when we were all together. Again, remember, please put here in the chat box for roll. And we're going to pick up in chapter 6, I believe. So we started talking about bonding with everybody here together last time. And we talked about, again, sort of the different types of bonding that we come across. And a reminder that we talk about, there it is, ionic bonding. So ionic bonding is always between a metal and a non-metal. And as we sort of talked about, what we always get in this situation is the metal will pretty much transfer electrons to the non-metal. The result of that is our metal then becomes the cation, which is positively charged, and the anion, which is negatively charged, as a result of the non-metal picking up those electrons. And really, one of the major things that you should remember when you think about ionic bonding, and it sometimes confuses people, is there is absolutely no sharing of electrons here. So again, what is holding that ionic bond together is simply the attraction between the positively charged ion and the negatively charged ion. And that is very different than what we get when we have some type of covalent bond that occurs. First off, a covalent bond is between two different things. It's between two nonmetals. And because really they are both nonmetals, they are both going to be pretty much in the same location on the periodic table, which means in terms of their electrons, they really are going to have very similar properties, which means basically overall, nonmetals want to hang on to their electrons. They also want to kind of gain electrons. So when we do put two of them together, really the best that will occur is some type of sharing of electrons. So again, that sharing of electrons here in a covalent bond is a major difference than what we see here in an ionic bond, where there is absolutely no sharing of electrons. Within a covalent bond and within sort of that sharing, the sharing may be equal sharing, which represents a type of covalent bond, which is known as a nonpolar covalent bond. Or really more simply, people just straight up call it a nonpolar bond, kind of leave the covalent part of it out, but they're basically the same thing. Or we may have unequal sharing of electrons. And unequal sharing of those electrons is a result of another type of covalent bond, which is referred to as a polar covalent bond. If I could actually spell there, covalent bond. Or again, in most cases, people really just call this a polar bond. Now, these are really sort of the three types of bonding that we talked about. I guess really non-polar and polar. And really, as we talked about, I think as well, there's sort of an extreme. On one end, we have an ionic bond where we have a complete transfer of electrons from one guy to the next. On the other end of the extreme, we have a non-polar bond where we have nice equal sharing of those electrons. And again, sort of in the middle, we have a polar bond, which is again not equal sharing of electrons, but not so unequal sharing that the electrons actually transfer. So sort of an intermediate, if you will, in terms of the bonding. We also talked about, and I think where we sort of finished up upon last time when we were all together here in lecture, was what we kind of used to help us determine, would we expect the bond between two atoms to be polar, non-polar, or even ionic? And really the overwhelmingly sort of property that we look at in terms of determining what type of bond that we get is really electronegativity. And if you remember, electronegativity is really the ability of an atom to bring electrons towards itself. And in terms of the periodic table, it increases as we go up and to the right on the periodic table, and it decreases as we go down, with fluorine being the most electronegative element that you could have. And we also saw towards the end there that there was a value sort of given for electronegativity that runs from 0 to 4. And remember that 4, which is pretty much what fluorine has, is the most electronegative you could have. And 0 obviously being not so much, right, in terms of electronegativity. And what we do with these values, if you remember, is we take the difference in electronegativity values, we simply just subtract the two values. And if you subtract the two values that you find on that table, and I think it's just a slide back, we were doing all these things. Again, this is the table we're referring to here of electronegativity values. You simply just take the two values for each of the elements that are involved in the bond, and you basically subtract them. And if you get a difference between 0 to 0.4, that is considered a nonpolar bond. Really, like 0.5 to less than 2 is considered a polar bond. And not perfect, but usually above 2. You can actually have a value less than 2 is still be ionic, but usually above 2 is definitely an ionic bond. And again, when we look at this table, like we did last time here, a couple of things that we talked about, if perhaps you don't have the table available to you, there is a lot of cases where, you don't really actually need the values. So first off, the ionic bond, definitely don't need the values, because if you see one is a metal and the other is a non-metal, it's pretty much going to be an ionic bond. So you don't really even need those values to figure that out. So always, if you see metal, non-metal, ionic, don't really need the electronegativity values. If we are looking at something where the two elements are in the same period on the periodic table, like I think we were looking at carbon and nitrogen, for example, here, and we look at carbon, which is right here, and nitrogen, which is right next door. And because they are in the same period or row on the periodic table, we do know just by the fact of their location that nitrogen should be more electronegative than carbon. And that's enough to tell us it's going to be a polar bond without even needing the numbers. Again, in that situation, we would also know that the arrow, which we typically use to indicate a polar bond, this dipole arrow, remember, points to the side that's more negative, and the other back end that makes like a plus sign is to the side that's more positive. So in this case, it would point to the nitrogen. We also looked at sulfur and oxygen. If we look at sulfur and oxygen, here's oxygen. Sulfur is actually right below it. And what we were talking about last time as well is, again here, because those two are in the same group, you don't really even need the numbers either. Just the general trend, we see that oxygen is higher up in the group than sulfur. And because they're in the same group, we will know that will lead to an electronegativity difference and definitely a polar bond. So there's a lot of times where you could really make a pretty educated guess in terms of polarity. Is it a polar bond or non-polar bond? By just looking at the general trend on the periodic table. We also talked about a couple of things just to watch out for. There is that sort of diagonal relationship, right, between carbon and sulfur, carbon being higher up, but sulfur being further to the right. So they sort of cancel their contributions. and they actually end up with the same electronegativity value. So, as long as you don't have some type of diagonal type of relationship, you might want to look at the values. But if you're in the same row or the same group, you pretty much can make a pretty safe bet that you would have a polar bond. And again, if you have a metal and a non-metal, it's a pretty safe bet that is going to be an ionic bond. Any questions on any of that stuff there we talked about last time? Okay, so I think that's where we left off. And again, we sort of talked about this, I think, with electronegativities. But as we could see from that chart, and as we talked about last time, essentially, guys with very different sort of electronegativity values do tend to make ionic bonds. And that's really why it's a safe bet when you pull a metal, which is essentially left on the periodic table, and a non-metal, which is upper right. These guys are very far away from each other, should have a very difference in electronegativity, and we would expect an ionic bond to form, as opposed to when we get into covalent bonding, we're really talking about everybody in the same location on the periodic table. So again, they have very similar electronegativity values, and that's why we get some sort of sharing happening, as opposed to a transfer of electrons. I know this says less than 0.5, so just so we're clear, 0.4 is the cutoff there. So kind of less than 0.5 would be 0.4. And again, the rest of the values there. Any questions on using electronegativity? Again, a reminder, we use electronegativity values and the differences in electronegativity values really to answer one question, and that question is, when I make a bond between these two elements, will I expect the electrons to be shared equally or unequally? And that's really sort of bond polarity is sort of what we look at it for. So earlier in this chapter here, we talked about ionic bonding and how to use Lewis structures to draw ionic bonds. We're now going to talk about really how to use Lewis structures to represent covalent bonding. And there's a certain orders at which you want to kind of do this. And let's talk about sort of the steps here that we definitely want to follow when we are doing Lewis structures for covalent compounds. You definitely want to kind of follow these steps, and it will lead you to sort of a correct structure. If you do it in sort of piecework, which I sometimes call it, and what that means is sometimes people want to draw each of the individual elements with their valence electrons and try to figure out, well, this guy has 5, so he needs to pick up 3 from somebody, and this guy goes over there and this guy goes over there, and try to figure out where the electrons go. Usually you'll end up with a wrong structure, too many electrons, not enough electrons, wrong bonds, and stuff like that. But if you follow these steps and sort of think about the electrons as, I have this many electrons, and what I need to do is distribute it to everybody in the molecule that I'm drawing, it usually does work out better than kind of going individually, trying to think about how everybody gets there. A couple of important reminders as we talked about bonding. Obviously, the octet rules in play here. So that is the goal of covalent bonding, is for everybody to get to 8 electrons around it, except for our good friend hydrogen, which, as we talked about, only needs to get to helium to hit noble gas configuration. So again, hydrogen should only have 2 electrons. A couple other important things. When we draw these things, we do want to make sure that we put these things in sort of the correct order. What I mean by that, the first thing you want to kind of think about is, what is the logical arrangement of how you would put those atoms together. Just logically speaking, if you're given something to draw where there's perhaps 1 carbon and 4 hydrogens, usually the 1 element's in the center, everything else is attached directly to it. If it happens to be something that I think you would maybe not know how it's put together, I would probably give you a hint. But for the most part, most of the stuff that we draw, something in the center, everybody else sort of attached to it. To help you decide what should go in the center, there are some general rules. First off, the least electronegative atom should occupy the center position. So in the center should go the guy that is least electronegative. We should never have hydrogen in the middle, because hydrogen, again, should only have 2 electrons. And a reminder, hydrogen should pretty much look like that always. Should never, I think I drew this earlier, never double bond to hydrogen, never triple bond to hydrogen, never put dots all around hydrogen. That is wrong. This is pretty much hydrogen and what it should look like. So if you find yourself doing any of those things, again, cross it out yourself, because it is probably wrong. Because hydrogen can only have 2 electrons, it cannot be in the middle. Otherwise, it obviously would have more than 2 electrons. Fluorine should not be in the middle either, because again, the middle guy should be the least electronegative atom. Fluorine is actually the most electronegative atom. So again, we typically do not see fluorine in the middle. Out of all this, number 2 here is really the most important sort of guy, and that is counting the total number of valence electrons. A reminder that the number of valence electrons for each element is equal to the group number. So everybody in group 1 will have 1 valence electron, group 2, 2, 3, 3, group 4 where carbon is 4, group 5 where nitrogen is 5, group 6 where oxygen is 6, and 7 and 8 going that way. So that is obviously the quickest and easiest way to figure out the valence electrons. We can sometimes come across a polyatomic ion, which are basically groups of ions that actually do have charges. They are ions that actually are covalently bonded together, but actually end up with an overall charge. So if we do have something with a charge, we need to adjust our electron count to make sure that we do end up with the correct sort of structure. And a reminder that if something has a negative charge, that means that it has gained electrons. So we need to add to our total number of electrons the charge. If something has a positive charge, it has lost electrons, which means we need to subtract it from our total. So that's a really important thing. You need to get the total number of valence electrons in the entire molecule. A reminder that that number is exactly the number of electrons you need to have in your picture. You can't have any more, you can't have any less. You need to hit it dead on sort of that number. Once you have sort of the logical arrangement of how things are attached, the next thing you want to do is actually make a bond. And we're going to make a single bond. I personally use a line to represent single bonds. You could use dots if you wanted to, but again, most people will probably use lines. We're going to do 1 line from the center guy to each of the outside atoms. Once we do that, that will then use up a certain number of our total electrons. Any electrons that we have left at that point will go on the outside atoms. So we'll have some outside atoms at that point, and they go on as pairs of electrons. And we put them on as pairs of electrons until all the outside atoms are filled. What that means is all the outside atoms get 8 electrons, or if it's hydrogens, no dots. If you put all the outside atoms and fill up all the outside atoms with dots, non-bonding electrons, and you still have more electrons to put onto your picture, you then would go to the center atom. So we'll call this guy here X, the center atom. You would then go to the center atom and put them on as pairs. So again, single bond from the center to everybody. All the electrons are left after that point go on in pairs on the outside ones first until they are filled. If you still have electrons after you fill the outside ones, then you go to the center guy and fill them with dots. It is at this point you should run out of electrons. And once you run out of electrons, you do want to double check a couple of things. First off, you want to check that everybody has 8 valence electrons around them, except for obviously hydrogen. This should have 2. And if somebody does not have 8 valence electrons around them, it is at that point that you should try to fix that problem by double bonding and kind of exhausting all your double bond options, and then triple bonding if double bonds are sort of done. Now, you do not want to, what a lot of people seem to always want to do when they're drawing Lewis structures is right out of the box, I'm just going to start laying up some double bonds and triple bonds and stuff like that. So you definitely shouldn't double bond or triple bond out of the box. You should think about saving double bonds or triple bonds only if it's needed to fix a problem, like somebody does not meet the octet rule. So again, do not double bond or triple bond straight out of the box. Now it's a lot of words, so let's go through one here together to see how we put all those things in order. So really the first thing personally that I do is I calculate the total number of valence electrons. So here, nitrogen is group number 5 on the periodic table, which means it has 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which means each of them have 7 valence electrons. That's 21, and 5 is 26 valence electrons. This number is really important because when I am done with my picture, that is exactly to the number how many electrons I need to have. I can't have any more or any less. I got to be at 26. So logical arrangement, like I was saying before, in a situation like this, I got 1 nitrogen and 3 fluorines. So logically speaking, nitrogen would be in the middle, fluorine would be on the outside. More importantly, when we look at the periodic table, nitrogen, oxygen, fluorine, nitrogen is to the left of fluorine, and we know fluorine is the most electronegative atom, so it should never be in the middle. So we would put nitrogen in the middle because it is the least electronegative atom. We would put a fluorine on 3 sides. And to answer maybe a question somebody might have at this point, the answer is yes. And the answer yes to the question of, does it matter if I put the fluorine on the bottom or if I laid the fluorine up on top? And the answer is it doesn't matter. So you could have arranged it this way and it's all good. So it doesn't really matter whichever way you want to arrange sort of that third fluorine on top or bottom. It's all good. Once we have it logically arranged, once we got it, how many electrons we need, we're going to start drawing here. We're going to make 1 single bond from the center to each of these guys. Remember that each line represents 2 electrons, which means that is 2, 4, and 6 electrons that I have used. If I subtract that from my total, that tells me that I have actually 20 more electrons to put onto this picture. The 20 electrons, again, will go on the outside atoms in pairs of electrons. So that is 2, that is 4, that is 6. That fills this guy up with 8. That is 8, 10, 12. That fills this guy up with 8. 14, 16, and 18. That then fills this guy up with 8. At this point, I have put on there 24 electrons. I still got 2 more to go. Since everybody on the outside is filled, I now move to the center atom, which is the nitrogen, and I also put it on as a pair of electrons. I have now placed all 26 of my electrons. The last thing that I want to do is to make sure that, everybody has 8 electrons. So if we look at the fluorine, 2, 4, 6, and 8. Every fluorine is exactly the same, 2, 4, 6, and 8, 2, 4, 6, and 8. When we look at the nitrogen, we have 2, 4, 6, and 8. Every single one there has 8 electrons. We have placed 26 electrons on this picture. This would be the correct Lewis structure. Any question on those steps? All right, let's,
Professor, would you mind doing one more like that? Sorry.
yeah, we're going to do a few more examples.
Oh, okay. Thank
Any
you.
questions on this one here? No. Yeah, we're going to do a few more here before we're done drawing, obviously. So,
Oh, great. Thank you.
okay. Yep. All right, let's take a look at another one here. There it is. All right. I tell you what, why don't you give this one a go yourself, and then we'll talk about it. So again, follow those rules and see what you come up with. Okay, let's take a look and kind of see how you're progressing and kind of help you out probably with maybe where you had to stop. So if we look at this, the first thing we want to do is, again, get the total number of valence electrons. So we know that carbon is group number 4 on the periodic table, which means it's got 4. There are 3 oxygens, which means each oxygen is 6 from group 6. Now, in this particular case, this is carbonate, and it has a -2 charge. So remember that the minus means that it gained electrons, and the 2 is how many electrons it gained. So in this case, we do need to add 2 to our total here, again, because of the -2 charge. Otherwise, you will be short some electrons. And if we do all that, that looks like 18, 20, 24 valence electrons. Again, here, if we kind of look at the periodic table, we see carbon is here, oxygen is here. Carbon is less electronegative than oxygen, and it should be in the center. Again, there's only 1 carbon and 3 oxygens, so it does make sense to put it in the center. So logical arrangement would be carbon in the center. Again, our 3 oxygens around it. And just like the other one, if you wanted to, you could have put the oxygen on the bottom. It's all good. We are at this point where we're ready to basically make one single bond from the center atom to each of the outside atoms. That is now, each line represents 2 electrons, so 2, 4, 6 electrons we used. If we subtract that from our total, that's a lot of math there. That is 18 more electrons, I think, to go. Those 18 electrons will go on the outside atoms first, again in pairs. So here we go. 2, 4, 6. That is filled. 8, 10, 12. That oxygen is filled. 14, 16, and 18. I have now placed all 24 electrons. The thing that we want to do now is to make sure that everybody has 8 valence electrons around it. If we look at the oxygen, 2, 4, 6, and 8, all the oxygens are identical to it, which means all the oxygens obviously have 8 electrons around it. We can do that without erasing the whole thing here. There we go. Now let's look at the carbon, though. When we look at the carbon, it has 2, 4, 6 electrons. It does not have 8. So in this particular case, carbon is not good because it has less than 8 electrons. It has not met the octet rule. So we need to fix that. So can we fix it by putting some electrons there? And hopefully, you know, the answer is actually no, you cannot do that, because now what happens is we have a grand total of 26 electrons, which is too many. So we can't just add electrons to make it work. So this is the situation where once we place all of our electrons and we still have somebody that has not met the octet rule, we're going to try to fix it. And we're going to try to fix it by making a double bond. In this particular case, you have 3 options. You could double bond oxygen to carbon there, oxygen to carbon there, oxygen to carbon there. I'm going to do the top one. It doesn't really matter which one you choose. They're all the same. Can I just draw a line here to make a double bond? And again, hopefully your answer is no, you should not do that. And you should not do that because of two reasons. One, we're back to 26 electrons if we do that. And secondly, this oxygen on top will now have 2, 4, 6, 8, 10 electrons, which are too many. So when we actually make a double bond, what we are actually going to be doing is taking a pair of electrons and basically moving them in to make the double bond. And the result of doing that will give us a structure. If we do it there on top of carbon, we will now move those electrons in to make the double bond. We still have the other 4 electrons there on that oxygen. Absolutely nothing changed on the oxygens on the other side. They remain the same. And to make it look correct and right, since this thing does have a charge, we typically have brackets around it and the charge on the outside. What we have just done is keep a grand total of 24 electrons. So if we look at the electrons total, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. The single bonded oxygen, 2, 4, 6, 8. Single bonded oxygen on the right, 2, 4, 6, 8. Carbon in the middle, 2, 4, 6, 8 with the double bond. Oxygen on top, 2, 4, 6, 8. Everybody has 8 valence electrons, and we have a grand total of 24 electrons, and this would be the correct structure for carbonate. Question on that move there. Now, again, as I mentioned, you absolutely, if you wanted to, could have put the double bond there. And if you did that, you would get another structure that looks like this. The only real difference is double bond to the left. That would then leave this guy as a single bond. And our guy to the right, obviously, as a single bond as well. Again, we'll put a little. You could absolutely have double bonded to the right-hand side. And again, the only difference would be that the double bond would end up over here on the right-hand side. And single bonded everywhere else. All 3 of these structures are actually related to each other. They're sometimes related by this arrow that heads in both directions. These are what are known as resonance structures. And the reason we have resonance structures is for like really this situation. We could have made the double bond on the left-hand side. We could have made a double bond on top, or we could have made the double bond on the right-hand side. And the real reason for it is the double bond electrons are what are referred to as being delocalized, which means at some point in time, they may find themselves over here. At some other point in time, they may be up there in the middle. At some other point in time, they may actually be over there in the right. So whenever you have really an option like this where you can need to draw a double bond and you have more than one option for where you could put the double bond, you could draw another structure which is just as good and was referred to as a resonance structure. Do you have to draw all the resonance structure every time in a situation like this? The answer is no. If you were asked a question just like this to draw the Lewis structure, you could have drew any one of these 3 structures and they would all be correct. If you were asked to draw all the resonance structures, you should have drawn all 3 of these structures. So you probably won't be asked that in this class, but again, if you're asked just to draw the Lewis structure, any one of these guys would be correct. Any questions on that one there?
The brackets and the negative charge need to be included.
They do. So typically whenever you draw anything that has a charge, which are typically these polyatomic ions, because really polyatomic ions are covalently bonded things like we see here with the carbon and the oxygen sharing electrons, but they happen to have an overall charge. So typically speaking, it's very common practice to put the brackets around it with the charge on the upper right there. And again, for anything that has a charge associated with it.
Okay, thank you.
You're welcome. Other questions? All right, so why don't we try a few more here? Make sure. Actually, yeah. Let's go here. Let's do, why don't you take a few moments here and draw the following. Let's do SH2. Let's do CO2. Let's do SO2. Let's do N2. Why not? Let's do NH4 plus. Let's see here. And let's do SO4 2 minus. All right, so take a few moments here, draw a proper Lewis structure for each of these, and we will in a few minutes here or so take a look and see how you did. Again, try to follow those steps. If somebody doesn't meet the octet rule, try to fix it with a double bond. If double bonds don't fix it, try to fix it with a triple bond. They work the same way. You bring the electrons in and see what you come up with. Let's take a look. I know you may not be completely done, but let's see how you're progressing. Make sure everybody's on the right track here. So we'll start with the first one here. So again, we're just going to count up our valence electrons. So sulfur is group 6. There are 2 hydrogens, so that's 2 times 1. That tells us 8 valence electrons. Here, clearly, as we've talked about previously, we never put hydrogen in the middle, so we will go with sulfur in the middle. Hydrogen will be on the outsides. Following the same patterns we've done before, we're going to do a single bond to the center guy, to each of the outside guys. That is 2 4 electrons that have been used. I then have 4 more electrons to put in there if I subtract that. I am going to put those on the outside ones first, and I'm fairly sure nobody hopefully put any dots on the hydrogens. They are completely full at this point. Remember, hydrogen should not have any dots. That means we then follow our next rule, which is when everybody on the outside is full, we then go to the center and we do place those guys on as dots. So that is 2 and 4. And at this point, we have now placed all 8 of our valence electrons. If we take a look again, hydrogen has 2 on the left, hydrogen has 2 on the right, sulfur in the middle has 2, 4, 6, and 8 electrons with the non-bonding electrons and the bonded electrons, and we have a correct structure. Any questions on that one there? Coming to CO2, again, carbon is group 4. There's 2 oxygens at 6 each. That is 16 valence electrons. Again, looking at the periodic table, we see carbon is further to the left of oxygen. That means it is least electronegative, which means we should place the carbon in the middle. Oxygen's on the outside here. We're going to do a single bond to each of our carbons. That is 2 4 electrons used. We then have 12 more to go on the outside here. So 2, 4, 6, that's filled. 8, 10, and 12, that is filled. We have now placed a grand total of 16 electrons. When you look at this, you should see that the carbon is not good. It does not have 8. It only has 2 and 4 electrons. So we want to try to fix it by making a double bond. You could choose either side here. So remember, when we make that double bond, we're going to bring it in. And when we do that, we will end up with this. And now if we look at the carbon, it has 2, 4, 6 electrons. Better, but not 8. We have an option here to make a second double bond on this guy. And that is what you should do. You should try to exhaust all of your double bond opportunities before you go to triple bond. So in this case, we would then again bring in a pair of electrons on the other side. And when we do that, we will now lay up a double bond on the right to match our double bond we got going on there on the left. And we still have a grand total of 16 electrons. Oxygen on the left and right are the same. It has 2, 4, 6, 8 electrons. Carbon in the middle, 2, 4, 6, 8 electrons. This would be the correct structure for carbon dioxide. Any questions on that there? So again, in a situation like this, if you made a double bond and it kind of helped but didn't fix the problem, but you still have an opportunity to make another double bond, you should do that first before you jump to a triple bond. Any questions on those two?
Yeah, Professor Ifan, I got a little lost in those two lines that you had put for the CO2.
Okay. Making the
on
double
second.
bond?
Yeah.
Okay. So originally, once we placed all of our electrons, we were basically at this guy right here. And the problem with this guy was really the carbon. The carbon ended up at this point with only 2 and 4 electrons. So whenever we place all of our electrons and we need to fix a problem like that, what we need to do is try to make a double bond. So the first thing that I tried was to make a double bond on the left-hand side by bringing these electrons in to make the double bond like we talked about. And at this point, what we end up with is the carbon goes from 4 electrons to now 2, 4, and 6 electrons. It actually got better. It went from like 4 electrons to 6. But remember, the ultimate goal is to get to 8. So instead of on the left-hand side making a triple bond, because we had the opportunity on the right-hand side to make another double bond, that is what we did. So we took those electrons from the outside and brought them in to make another double bond. The result of that now gives the carbon in the center 2, 4, 6, and 8 electrons, which makes it happy. And all of the oxygens also have 2, 4, 6, and 8 electrons. So the goal here, remember, is basically to get to 8 electrons. And sometimes, as we saw in the previous example, it may just take 1 double bond to do it. Sometimes it may take 2 double bonds like we see here. And sometimes you may actually have to go to a triple bond to get everybody to 8. But again, the goal there is to get everybody to 8. And when we make a double bond or a triple bond, we're not adding electrons, but we're actually bringing electrons in to make those bonds.
Okay, got it. Another question.
Yeah.
Our end goal is to get 8. For some reason, my mind is emphasized on 16 instead of 8. Well, why 8?
8 is the octet rule, and really the reason for 8 is if you look at the periodic table. Let me just actually find some more scribble. Go here. If you look at the periodic table, right, group 8 on the periodic table, which is way at the end, that's our noble gases.
Okay.
And noble gases are chemically inert. They are extremely stable. And the goal of all bonding, both ionic bonding, covalent bonding, which is what we're talking about here, is for everybody to end up with the same electron configuration as a noble gas, which means they essentially will end up with 8 valence electrons around them. And that's really why 8 is sort of the magic number. The only one that doesn't need to do that is hydrogen, because if you look on the periodic table, this is hydrogen, which is 1. And just to the right of hydrogen on a noble gas is helium, which is 2. So all hydrogen needs to be happy is just to get to helium. And that's why we say hydrogen should only have 2 electrons, while everybody else needs to get to 8. And really the goal is there to get everybody to the same electron configuration as the noble gases. And that's a super stable situation.
Cool. Thank you.
Welcome.
Professor, I have a question.
Yeah.
So what if it were not to be like the double bonding, but what if we were to put like independent electrons, like 2 on top of C and then 2 on the bottom of C.
No, so you can't really do that. So if you're asking, like, are you asking like if we could just put like electrons here? Is that what you're asking?
Yeah.
You can't really do that because if you just put the electrons, we now have way more than 16. And that number is super important. That is all the electrons you have. So you can't just add electrons to get it to 8, because then you'll end up with too many electrons, more than you should have. So that's why we technically need to use the electrons that we have and bring them in so that more electrons could be shared with the center atom and allow the center atom guy in this case to get to 8. So remember, this number is almost the most important thing when you're drawing these pictures, is that number where you calculate how many electrons you should have, because that is exactly to the nose how many electrons your picture should have. You shouldn't have any more or any less.
Thank you.
You're welcome. Other questions? Okay, so let us take a look at the next one, which is SO2. I have to kind of come this way with it, I think. So sulfur here is 6. Again, here we have 2 oxygens, each has 6. That is 12 and 6, which is 18 valence electrons. Again, this number really important. We gotta have 18 total. Again, looking at the periodic table, we see actually oxygen and sulfur in the same group. Sulfur is lower on the periodic table in that group. That means it's the least electronegative, which means we should put sulfur in the middle. Oxygen's on the outside. Again, we want to follow the same pattern here, a single bond and a single bond. So that is 2 and 4 electrons that have been used. So if we subtract it, we're left with 14 more electrons to put on this picture. We will put it on the outside again in pairs. So that is 2, 4, 6. That guy is full. 8, 10, 12. At this particular point, we have placed 16 total electrons. Everybody on the outside is full, but we actually then have 2 more electrons we need to put. Those now go to the center atom, and they are also put on as pairs. So they're put on here as a pair. At this point, we have now placed 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. We're out of electrons at this point. We want to make sure that everybody is okay. And hopefully, if you look at this structure that I'm looking at and I just drew, you will see that the sulfur here is not good. It actually only has 6 electrons on it at this point. Again, 2 on top and 2 and 2 on the left and right hand side. So again, here we can make a double bond to try to fix it. We have oxygen on both sides. We could just try either side you like. We're going to do that because we can't add any more electrons. We need to borrow some from here and basically bring it in to make our double bond. When we do that, our double bond will now end up on the left-hand side. Our sulfur and our oxygen. Now, when we look at it, we still have 18 electrons. The sulfur in the middle has now reached 8. 2, 4, 6, and 8 is now good. And the oxygen on the left there also has 8. And this would be a correct structure for SO2. We also could have, like we talked about with CO3 2-, we could have done the double bond actually on the other side. And you could have drew a resonance structure for that, which would look like pretty identical, except that we double bonded the right-hand side. And again, here we would have 18 electrons and a double bond. If you follow our rules here, you will end up with the correct structure, which does have these non-bonding electrons on the central atom. if you don't follow our thing, our sort of path here, you'll probably end up like a lot of people will do on this one, double bond both sides with no dots, and that would be incorrect. So again, sort of the placement of those electrons on the outside ones first, and then the center one is really important to make sure that you do place sort of your non-bonding electrons. Again, these are both resonance structures. You would not have to draw both of them. You could have drew this structure and it would have been fine, or you could have drew the one on the bottom and it also would have been perfectly fine as well. Any questions on that one? All right, then let's take a look at the next one, which is nitrogen. So this one is 2 times 5 for the nitrogens, which is 10 valence electrons. In this particular case, there is no center atom, so there's just 2. So whenever you have 2 atoms, you essentially just place them side by side. And you actually could follow the same rules that we've been doing, which means we'll just connect them both with a single bond. That gives us 2. That leaves us 8 electrons to go. Again, following what we've done before, we will put those 8 electrons on the outside on the right here. 2, 4, 6, it's full. And then the other 8 will go over there. We have now placed all 10 of our electrons. And again, if you're looking at the structure, the way it's drawn, hopefully you could recognize that this nitrogen over here is not in a good position as it only has 2 and 4 electrons. It is short 4 electrons. So we could try to fix this by doing a double bond. In this case, we really only have one option. We're going to take some electrons in and try a double bond. And if we do that, we end up with this picture here. Again, the nitrogen on the right is all good. It has 8 electrons. Nitrogen on the left, not so good. It got better. It went from, again, 4 here to 6, but it only has 6, 2, 4, 6. So at this point, there is no other option at this point. There's no other way to make a double bond. So now we need to make actually a triple bond. So since a double bond did not fix the problem, we're going to make a triple bond. Works the same way. We're not going to add electrons, but instead we're going to take some electrons and bring them in to make the triple bond, just like we did the double bond. And now we will end up with a picture that looks something like this. And now when we look at each of the nitrogens, they actually each now have 8, 2, 4, 6, 8, and 2, 4, 6, 8 on the right. And there's still only a grand total of 10 electrons. And that is why nitrogen is actually a triple bond in this case and needs to get to a triple bond to allow both of the nitrogens basically to get to the noble gas configuration. Any questions on that? I'm going to flip the page since I'm out of room here. We'll do the last 2 on the next page here. That was NH4 and SO4. So let's take a look at these 2 guys here. NH4 plus. Again, nitrogen is 5. There are 4 hydrogens, each at 1. And here we do have a plus. So remember, when something gets a positive charge, it has lost electrons, which means in this case, we will be subtracting 1. And that will give us 8 valence electrons. Nitrogen's got to be the guy in the middle because we cannot put hydrogen in the middle. So we'll just arrange our hydrogens around. Again, we're going to do a single bond to each of these. At that point, we have now used 2, 4, 6, 8 electrons. We are good at this point. So nitrogen has 8. Each of the hydrogens have 2. It does have a charge, so we're just going to put a little bracket and a charge around it. Any questions on that one? All right, the last one that we had there was SO4 2-. Again, sulfur is 6. There's 4 oxygens at 6 each. Here we have a -2 charge, which means it has gained 2 electrons. So we need to add 2. That is 24, 26, 32 we'll go with. Here we have sulfur and oxygen. Again, as we saw earlier, they're in the same group. Sulfur is lower, which means it's less electronegative. And there's only 1 sulfur, which probably logically would be the guy in the middle. Everybody else is directly attached. And by the way, most of the things are like this. Everything is directly attached to the middle guy. There's no weird, like everybody's lining up this way or anything like that. You know, so usually you got a center guy and everybody's sort of attached to it. We're going to do our single bond all the way around. That is 2, 4, 6, 8 electrons. So we kind of subtract that off, do a little math. I think that's 24 left. They will go on the outside in pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 at that point. I have now placed all 32 electrons, each of the oxygens 2, 4, 6, 8, the sulfur in the middle 2, 4, 6, 8. Everybody is technically good and meets the octet rule. And this would be your proper structure here. Any questions on how to draw Lewis structures? Hopefully you can kind of see it's kind of the same steps. You just want to kind of follow those steps. Any questions on any of that? All right, let's see here. So we talked a little bit about resonance structures earlier as we were just drawing these Lewis structures, but there's also something to look at, which is bond length. And you by no means need to memorize any of these numbers. But what we do see when we look at the comparison of, say, a carbon-carbon single bond to a double bond to a triple bond, the single bond is about 154 picometers in distance. When we put a double bond on, everybody comes in a little bit. The distance between the carbons gets smaller, is 133. When we put the triple bond on, everybody comes in even closer at 120. And we see that pattern even with our nitrogen here, carbon and nitrogen. Single bonds 143, 138 for a double bond, and 116 for a triple bond. So the general pattern that we see is a single bond is the longest. And as we bring those electrons in to make a double bond or even a triple bond, it brings the atoms in that bond closer and closer to each other every time you basically put another bond on. The result of that is, in terms of bond strength, we do see that a triple bond is actually stronger than a double bond, and a double bond is stronger than a single bond. And it's not like a double bond is twice as strong as a single bond or a triple bond is 3 times as strong. But the general pattern is triple bond stronger than a single bond and also stronger than double bond. I relate it usually to like a brand new pencil, right? You take a brand new pencil out of the box, it's nice and long, you could snap it, no problem. You take a couple of chemistry tests, you're left with an eraser and like a nubbin, like that big of a pencil. Very hard to try to break that pencil in half because everything's really compact and close to each other. And the same thing happens as we drop that triple bond in there. Everybody's very tight to each other and very hard to sort of break. So the relationship is longer bond, which is a single bond, is the weakest. Shorter bond, which is a triple bond, is the strongest. Now, we talked about resonance structures as we were just drawing some of those. And again, a resonance structure is usually indicated by this type of arrow. And we do, for the most part, draw these structures as we saw, like in carbonate or SO2, where really we have more than one option as to where we could do a double bond. And you could draw an equivalent structure by really just moving the double bond around to anywhere it is possible to occur. And Here again was the example for carbonate. You don't have to worry about the charges. But again, we could double bond to the top, to the left, to the right. Again, as I talked about, really those double bond electrons are just moving around from one place to the next. So at any given point in time, they may be there or there or there. So we could draw 3 individual structures to sort of describe what is going on. Again, you don't have to draw all the structures unless you're asked to do so. And again, I don't think you'll be asked to do so. Benzene ring, we'll see in a later chapter as well when we talk about organic chemistry. But a benzene ring looks like this. It is all carbons here. Everywhere here is a carbon. And there's 3 double bonds. You could also move the double bonds to the other side. And most often, the way we will see it a lot in our book and stuff is they'll actually just draw a little circle to indicate that those double bond can kind of move from one side to the next. Now, let's talk a little about exceptions to octet rules, and let me be really clear that everything in this class will obey the octet rule, but there are some exceptions to the octet rule that we sometimes come across, but you should never draw those in this class because we will do everything that obeys the octet rule. There are certain elements that can be very happy with less than 8 around them, and those are guys which basically have what is referred to as an incomplete octet, which basically means they're electron deficient. They're perfectly fine with less than 8 around them. And really the one that you see the most of the time is actually the guy on the bottom there. Beryllium technically, but things that contain boron. Boron is known for being perfectly fine like we see there with just 6 electrons. And it's a very common sort of arrangement for it. Again, we won't have any sort of incomplete octet in our class, but that is an exception to the octet rule. And another exception to the octet rule is an odd number of electrons. Odd number of electron means like at NO or NO2, we end up with 1 unpaired electron, sometimes referred to as free radicals. Maybe you've heard of that. In chlorine chemistry or atmospheric chemistry, chlorine sometimes does that a lot. And they're very reactive because they only have 1 electron. So they're trying to fix that. So they react very quickly and stuff like that. Again, we won't see that exception here. The one that you see the most in chemistry, but not in our class, is the expanded octet. There are certain ions that can actually go over 8 electrons and be perfectly happy. And if you look at the periodic table where sulfur is to the left and to the right and down, those guys have the ability to do that because sulfur is on the 3rd period, and the 3rd period is n equals 3. And on the n equals 3 level, there are s orbitals, there are p orbitals, and they do have d orbitals available to them to basically house the extra electrons. So although they may not be using them, they have the d orbitals available to them to house those electrons, and they can sometimes go over it. So for example, SF6 is an example. You basically would have, I won't draw all the electrons on the fluorines, but sulfur is okay with 2, 4, 6, 8, 10, 12 electrons around it because it has those d orbitals and is able to do that. So for us, you just need to know what the 3 exceptions are, but everything for us will obey the octet rule. So you should always obey the octet rule in this class. But in reality, there are things that can go less than 8, and there are guys that can go more than 8. Any questions on that there? Again, we won't have any of those exceptions that she has to draw. Okay, so we're going to talk about geometry here. And we can basically use Lewis structures and the central atom to help us decide what is the sort of 3-dimensional geometry here of the molecules that we draw. And the theory that we use, or the basis of this approach, is what is sometimes referred to as the valence shell theory. And the idea is ultimately, when we make bonds, there are electrons near electrons. These guys are both negatively charged, which means they really do not want to be near each other. And what ends up happening is they cannot really escape because they're locked in the bond. So the best that they could do is try to move as far away as possible, depending on the bonds that are there, the electrons that are there, and sort of get to a place where they're like, all right, I don't really want to be near you because you're negatively charged, but I'm okay. We'll kind of keep our distance. And what ends up happening is as those electrons and bonds are trying to move from one side to the next and get away from one another, they end up messing with the actual shape of the molecule, the molecular geometry of it. So as one thing moves in a molecule, because everything's bonded together, other things start to move with it. So we do Vesper, which is valence shell electron pair repulsion model. And we're going to see two types of molecules. One where you draw the Lewis structure and there are no dots on the center atom. And that means that there's no non-bonding electrons present. And we'll see some where there are dots on the center atom. And that means that we will see some that have non-bonding electrons on the center atom. When we do geometry, it basically is all about the center atom. That is the most important one. And the most important rule to worry about for us is number one here. If you draw a Lewis structure and you have a double bond or you have a triple bond, we count these guys as one electron pair and also one bond. So one electron pair and one bond is what we treat double bonds and triple bonds. They're essentially thought of, even though they're double bond and triple bond and there's more electrons, is thought of as they are moving basically as one. So that's the major important thing to keep in mind. And we do that only for when we're doing this geometry here. We double bond and triple bond basically counts as one. Let's start with really the simplest ones to do. And of all the letters and numbers on here, don't worry too much about it. But the simplest geometry that you could have occurs from a diatomic molecule. Things like H2, F2, HF, HCl, O2, N2. No matter what happens when you have only two atoms present, there really is no center atom. So basically, when you only have two things, they are connected basically by a straight line. So when you have a diatomic molecule and you're asked, what is the geometry? The answer is linear. It's basically a straight line is the only way that you can arrange those guys. As you can see here, every single one of these that I drew, the geometry would be linear. Doesn't matter if it's two the same, doesn't matter if it's two that are different, doesn't matter if it has a double bond or a triple bond. If there is just two atoms present, the geometry will always be linear. The only way to arrange them basically is in a straight line opposite of each other. Any questions on that one? Now, when we get to three or more atoms involved, we do get a couple of different geometries that we're going to talk about. And we'll do this here. I'll just talk about what that is here. One geometry is what is referred to as the electron pair geometry, or electron group geometry. That describes how the electron pairs around the central atom are arranged in three-dimensional space. The other name for the geometry is what is known as the molecular geometry, or sometimes referred to as the shape. And that describes as a whole what the actual molecule kind of looks like in terms of its geometry and shape. So let's take a look at this one. This is beryllium chloride. This is actually an incomplete octet. Here's what we want to count. We want to go to the center atom always. We want to look, and I see 1 and 2 electron pairs. I see 1 and 2 bonds. So something with 2 electron pairs, the electron pair geometry will also be linear. Basically, those guys are going to decide, I'm going as far away from each other as possible, these guys. And the molecular geometry will also be linear. It is basically a bond angle of 180 degrees. So those 2 chlorines that are bonded to the beryllium go, I do not want to be near you. I'm going to go this way. This guy is going to go this way. And they end up basically being able to spread out at opposite ends of each other and end up with a electron pair geometry of linear and basically a molecular geometry of linear, which again is 180 degrees apart. The next example is a central atom where we have 3 things attached. Again, here, the electron pair geometry and the molecular geometry. We go to the center atom. It's got 1, 2, 3 electron pairs. It also has 1, 2, 3 bonds. Something with 3 electron pairs has an electron pair geometry of trigonal planar, sometimes referred to as triangular. Because these are all bonding electrons, the molecular geometry actually ends up being the same, trigonal planar. They basically, because we have the 3rd bond in there, they could only get so far away from each other. They kind of keep some distance from each other. Because of that 3rd bond, these guys can't get a full 180 degrees apart. So they get 120 degrees apart. It's called trigonal planar because basically it makes a triangle in terms of how they arrange each other. Again, 120 degrees apart from each other.
Professor, I have a question.
Yeah.
So how do we know when they're bonding electrons?
Bonding electrons are always, the lines are when you have basically 2 dots and 2 elements on either side of it. So these guys are bonding electrons within a bond. Non-bonding electrons are the dots. So those don't have any element on the other side. Those would be non-bonding electrons. Bonding electrons are typically always the lines are, if you did this guy with dots, it is these guys here. And what distinguishes it as bonding is I see an element there and an element there on opposite sides of the electrons.
So what determines like the degree?
It's basically how far they need to get away from each other, basically. So in this particular case, what ends up happening, you know, we have these sort of fluorines here. And these bonding electrons here, here, and here really don't want to be near each other because they're all electrons. So what happens is this guy goes, I'm going to get away from you. This guy goes, I'm going to get away from you. And this guy kind of goes, I'm going to hang out here. And the result of that is the fluorine stays on top. The guys over here spread out as far as they can from each other. They can't come any further, otherwise they're going to come too close. So they want to come back. But this guy cannot swing up any higher because he doesn't want to get too close to the guy on top. So they eventually will come to a rest in a situation that is optimal for their spacing. And in this particular case, when you have 3 electron pairs and 3 bonds, the optimal arrangement is this trigonal planar or triangle type of arrangement where it's 120 degrees apart.
Okay, thank you.
Other questions? So we'll continue on here with a central atom that has 4 things attached. And that is a very badly drawn one here. Let me actually redraw it correctly here. Not sure what happened there. All right. So again, our electron pair geometry and our molecular geometry, our shape. Here we would look at the carbon in the middle. It's got 1, 2, 3, 4 electron pairs. And it also has 1, 2, 3, 4 bonds. Something with 4 electron pairs will give a shape which is referred to as tetrahedral. And basically, because we have the 4 bonds, same idea, they want to kind of keep their distance from each other. So they are going to kind of spread out in this tetrahedral arrangement. And the molecular geometry will also be tetrahedral. And it has a bond angle of about 109.5. Tetrahedral is kind of like a triangle on the sides and kind of like a pyramid shape on the bottom. And again, that is tetrahedral. Up to this point, when we look at the names of the electron pair geometry and the molecular geometry, both of the names are the same. So they're the same there, they're the same there, and they are the same there. And what all 3 of these guys share in common is when you draw the Lewis structure and you look at the central atom, there are no non-bonding electrons. So no non-bonding electrons, the dots basically. And whenever there's no non-bonding electrons on the center atom, both of these names, the electron pair geometry name and the molecular geometry name, will be the same always. And that's because you're only dealing with one type of electrons here, which are bonding electrons. So as the bonding electrons move, there are actual elements on the other side that move with them. When we start to introduce non-bonding electrons, we actually see a change in the 2 names, and the change in the name happens with just the molecular geometry name changes. And the electron pair geometry stays the same. So if we look at guys that have non-bonding electrons, we get a few different interactions that occurs. We could have bonding electrons near bonding electrons, which is okay. We could have non-bonding electrons, which are the dots or lone pairs, near bonding electrons, which is not so good. They want to get away from each other. And really the worst case scenario is when you get non-bonding electrons or lone pairs near each other. They want to definitely get as far away from each other as possible. So when we start to see non-bonding electrons on the center atom, we end up seeing different name in terms of the molecular geometry. So let's take a look at one here, which is SO2, and I think we drew it just a second ago. And if we redraw it real quick here, it will look something like this. We have our electron pair name and our molecular geometry name. We look to the sulfur. It has, in terms of electron pairs, it has 1 electron pair here, 2 electron pairs here, and 3 electron pairs here. Double bond count has only 1 electron pair. In terms of bonds, it has 1 bond here. And again, the double bond only counts as 1. So that is 2 bonds. Again, the electron pairs determines the geometry of the electron pairs. And it has 3, which means it is still trigonal planar. But now we have bonding electrons near bonding electrons and non-bonding electrons near bonding electrons. And again, in this situation, you have your oxygens, and they're like, I definitely don't want to be near your non-bonding electrons. So these guys are going to try to move away from each other, but they can't get too close to each other because they're also bonding. And what ends up happening is they move away into a shape which is known as angular, and it ends up being a shape that looks something like this, kind of an angular type of shape, as they move away from those non-bonding electrons as far as they can, and the overall shape ends up being angular. Some people will call this bent angular, but we will go with basically angular is a little bit less than 120 degrees, but we do see the difference here in the molecular geometry because of the presence of these non-bonding electrons. Any questions on that there? So I have 2 more to go, and I'm a little bit over, so I'm just gonna finish these 2 out, and then we'll wrap it up here. So NH3 is an example here. We look at our electron pair geometry and our molecular geometry. If we look at the nitrogen, it has 1, 2, 3, 4 electron pairs. It has only the 1, 2, 3 bonds. Again, 4 electron pairs is the same electron pair geometry, which is tetrahedral. Again, here we have those non-bonding electrons on the nitrogen, and we have those hydrogens, which decide we want to definitely get away from each other. So they end up in a shape with our non-bonding electrons up on top, which is known as trigonal pyramid. Kind of makes like a triangle and a pyramid shape on the bottom. And this is trigonal pyramid. And again, it is the presence of those non-bonding electrons near the bonding electrons, which make those hydrogens basically move, and the overall shape changes. So again, electron pair geometry name stays the same based on how many electron pairs there are. Molecular geometry does change because of the presence of the non-bonding electron pairs. The last geometry that you need to know for this class is something like water. And in water, we look at our electron pair geometry name and our molecular geometry name. We look at water, it has 1, 2, 3, 4 electron pairs around the central atom. It has 1 and 2 bonds. Again, here with 4 electron pairs, it is tetrahedral as the electron pair geometry. This guy has everything in terms of worst case scenario. It has bonding electrons near bonding electrons. It has non-bonding electrons near bonding electrons. And it has non-bonding electrons near non-bonding electrons. These 2 guys try to go as far away as they can from each other. The result of that is as they move out, the hydrogens basically move down, and it ends up in a shape which is referred to as bent or V-shaped. So the best way to do geometry is to sort of memorize electron pairs and bonds and the names that go with it. And here's a table similar to the one you're finding in your book. You will be responsible for only the molecular geometry name or the shape, which is like this name. So you only have to know for lecture the molecular geometry name. Again, the best way to do it is how many electron pairs, how many bonds, basically. So that's what this is basically number of electron pairs and number of bonds. Any questions on that there? All right, we will lay it up there. Thank you for hanging out. Sorry.